Everybody, we are the Pentecost team. We are from Barcelona, Spain, and we are here to present the ACC2011. My colleague Javier and me, Jordi, will present this plane. Let me first say that we have a lot to say and not much time, so we will go a little fast. If you have any question at the end of the presentation, ask us. During the presentation, first we will introduce you to the project and also to the team. Then we will explain you how we have organized the working time. Then Javier will explain the final design of the plane. And finally, we will sum up the conclusions. As all of you, we are here to participate in the Air Cargo Challenge 2011 and to be competitive in this contest. And for this, we have designed, built, and flown a model aircraft capable of lifting as much payload as possible. For you to know a little bit about the Pentecost team, this team was founded in 2006 to compete in the first international edition of the Air Cargo Challenge in 2007, held in Portugal. We have competed twice in the Air Cargo Challenge, 2007 and 2009, and after 4 years, the team has grown to 35 students divided in 5 projects. The Pentecost team ACC2011 group, our group, represents the UPC, Tarrasa, and Catalonia in competition. I assume that you may know the specifications of this competition. So basically, what we have done is to translate these specifications to several requirements that our plane must meet. Let's now talk about the working groups. We have divided the project in 5 main areas.
My name is and in the name of the Munich Air Cargo Challenge team, I would like to welcome you to our oral presentation. First, I will tell you a bit about our team, and then we will get into the interesting part, the preliminary aircraft sizing, the design, and the test flight. This is our team. We are 7 members and we are sponsored by Airbus and Step 4. The members of our team are from the 2 student organizations Avion Munich and AK Modell Munich. The AK Modell Munich has a lot of experience with building aircraft models, and the Avion has a lot of experience with organization and stuff like that. So, but the aircraft design is influenced by members of both teams, and our work together was really fruitful. On this year, I would like to thank our sponsors, Airbus and Step 4. Airbus has given us financial support, and Step 4 has allowed us to use their machines to make our molds. Here are some pictures and a video from the maiden flight, which was yesterday, and the second flight this day. Okay, very short maiden flight yesterday, and we don't show a video, but today was a very successful flight. Yes, okay. There we go. On this flight we had a payload of 4.5 kilograms loaded to the aircraft. The flight was 5 minutes and 40 seconds long, and we landed successfully, as you can see. 40 seconds. A very successful test flight. Now we go to the preliminary design, and I will give over to my colleague Stefan.
Hello. Okay, in one of our first design meetings we had to choose a proper configuration. We considered 3 different configurations. The first one was the tracking configuration. You might have seen this picture already.
Very good.
The advantage of the tracking configuration is that a lot of information is available, it's predictable, and it's quite easy to build. The second configuration was the canard configuration. The canard can provide additional lift, but the interference effects can reduce the lift of the main wing, and this lift reduction is hard to predict. The last configuration we considered was the blended wing configuration. It provides a large wing area, and maybe it leads to less weight due to a lack of a fuselage. But also this configuration might be hard to realize, so we decided to build a tracking configuration. But we choose the center of gravity so that the tail should not produce downforce. The next step was to examine the propulsion system. First, we used the program Java to calculate the total propeller diameter and pitch based upon the data of the prescribed motor. Then we looked which props are available and bought some, and verified the simulation results at the wind tunnel. With the data from the wind tunnel, we could start our preliminary sizing. Therefore, we used a MATLAB tool, which we also used in the previous two competition that was adapted to this year's regulation. And this tool basically simulates the takeoff run. Oh. Yeah. What it does this by iterating over different payload and aircraft dimensions, and so tries.
There is also one female team member which is not in the picture because she is ill right now. And Miguel Silvestre. And then we, of course, divided the team members in the several tasks that we will have to perform. The team schedule, in gray we have the schedule that we built up at the beginning, and in red we have the actual schedule that we made to follow, that we actually followed. And so now I will present the part of the problem analysis, problem definition, and that's the way we do our conceptual design. So from the beginning we do some calculations. Of course we have it was very windy. It was 5 meters per second and the soul speed was 5.7 with this cargo. So, quite hard landing, but we have
hello everyone, I am Fanny from Tsinghua University, Beijing, China. And now please allow me to give a presentation of our Air Cargo Challenge 2011 project. This is our team. Our abbreviation is AIR. It's for Aero Innovation and Realization Center. And all the team members are bachelor candidates from the university. And our professors are, our advisors are professors from the School of Aerospace. And our coach, also the pilot, also our most guider is the National Championship of F3A. And our team is a very prestigious and a small collective. Our ACC project follows such steps: aerodynamics, structure, manufacturing, and as we can see, this is the Comet with empty load. And you can see that it is not so balanced, and because it is too sensitive to the center of gravity, and yeah, it is the biggest problem for the Comet. When we have the very heavy load on it, the problem was amplified. So we decided to abandon the Comet configuration. When the configuration is decided, we have to decide several parameters and the limitations from the regulations. Limitations are the biggest limitations are the box size. So we write a MATLAB program to optimize the geometrical parameters. This is the flowchart of our program. In order to achieve maximum proportion, we have tried all the available propellers. At last, there is also limitations on current, so we choose the 13.6 propeller because it has the maximum current of 39.6, and the carbon fiber propeller was the lightest. When propulsion is decided, we have to select airfoils. We have considered 5 airfoils. At first we want to use S1223, but first it was very hard to fabricate because it's very curved, and also we have previous experience of using this airfoil. It was very slow, and for our pilot, it is very hard to manipulate. And for the heavy payload, manipulate performance is quite important to prevent the aircraft from crash. So we decided to use FX76 and P12. The reason is that we have applied this airfoil in our previous national competitions and have very good results. And when we optimize the geometric parameters, we always thought about the shorter takeoff distance, the 60 meters. So we have to reduce the wing load. In order to reduce the wing load, we have to enlarge the wing area with the wingspan limitation, I mean the box size. So we must have low aspect ratio. This is the result of the geometric optimization. As we can see, aspect ratio is very reasonable. And we use vortex method to plot the distribution of pressure on both upper and lower surface to verify. This is the view of our final prototype, and the photo is the real prototype. Now let's go into the structure design, and the scheme we use the most structure to build most of the structure. We use balsa and other kind of wood because we can make it very large since we have to achieve a very large wing area. And the wood is very light, and in some critical points with very big compression or the tension, we use fabric, we use carbon fiber or other kinds of compound materials to reinforce. And this is our fuselage structure. As we can see, we use cross. We use cross section in every bulkhead. And during the flight, the payload was fixed on the payload cases, and use 6 screws to fix on the stringer. And the stringer will bear most of the weight and translate this weight to the bulkhead. And the bulkhead will translate weight to the main spar. The main spar will be very strong. So that's why we design this structure is because we don't have to build fuselage very strong or very large, and we can reduce weight. And we will build the landing gear just directly under this payload cases. And then during takeoff and during landing and the flight, the impact of the payload will directly shared by the payload cases in the landing gear. And this is our manufacturing process, and we use laser cutting machine to cut precise shape of the airfoil, and assemble these parts by rapid rule. And plastic skin was used to maintain the shape. That's why another reason to use wood is that we can fabricate prototype very quickly, because it's very quick to glue the wood and very quick to cut the shapes. This is the calculation of the main spar. I mentioned before that main spar bears most of the payload's weight. That's the calculation of some critical points. We have carried out several loading tests of the main spar because it bears the most of the weight. The first two we achieved 12 kilogram and 11 kilogram, and we thought that was not enough because when we for the second loading test, the main spar has a little bit damage after 11 kilogram, and we insert a carbon fiber on the upper surface of the main spar, and where is the critical point for compression. And after this improvement, we can achieve a loading test of 14 kilogram. That's very successful. Okay, after all this, we have to test the flight. At first, we test our camera configuration. We abandoned the camera configuration at first, but it also gave us experiences, which I will mention later. And for the regular configuration, we have the first prototype crashed at the payload of 9 kilograms because the control surface was too small and shows a very poor manipulative performance. And after it crashed, we just enlarged the control surface after this test, we achieved much more payloads to the sky, but we also find some problems that at first it cannot take off in 60 meters because the large friction, and also it's not efficient for us to load the payload on the cargo cases. So we do the following improvement. For the landing gear, why it cannot take up in 60 meters is mainly because we use sponge weir at first. It brings about very large friction during taking off stage, and we use a nylon. We use a nylon wheel instead of it, and reduce the friction considerably. And use carbon, and also at first we use wood to build the landing gear, and test shows that it cannot bear the impact during the landing. And then we use the carbon fiber and reinforced by a stainless wire. And also, this is a little tool. With it, we can load the box very quickly in maybe 1 minute and a half, I think. Please allow me to present our final test of the regular configuration, and it's real. It achieves 12 kilograms. Take to the sky and end with a beautiful landing. Please enjoy.
Discussion today.